Let's talk about infinity for a second. You'd think if you start adding up an infinite number of things, the sum would just get bigger and bigger forever, right? Well, what if I told you that an endless list of fractions can add up to a perfect, simple whole number? It's one of the most beautiful little puzzles in math, and we're going to solve it together.
And that number is 2. I know, it sounds completely impossible, right? How can you keep adding and adding and adding and land on something so clean? Just stick with me, because the way we figure this out is like a really clever piece of detective work.
So, how does this work? How can this endless stream of fractions, each one getting smaller and smaller, somehow land perfectly on the number 2? Not a bit more, not a bit less. To figure that out, we first need to see exactly what it is we're adding up. Okay, so here's the official problem we're trying to solve. The infinite sum of the reciprocals of the triangular numbers equals 2. Now, reciprocal is just a fancy way of saying 1 divided by that number. Sounds a little intimidating, I get it, but we're just going to take it one step at a time. First things first, what does this sum actually look like? Here it is, 1 over 1 plus 1 over 3 plus 1 over 6 plus 1 over 10, and on it goes, literally forever. Now, the key to this whole puzzle is hiding in plain sight. It's the numbers on the bottom, 1, 3, 6, 10, 15. Those are not random. They have a beautiful, elegant structure, and to solve this thing, we need to investigate them.
All right, time to do a little detective work. The numbers at the bottom of our fractions, our persons of interest, if you will, are what mathematicians call the triangular numbers. And, they get their name from exactly what you'd think.
You can literally arrange them as dots, and they form these perfect, neat little triangles. See? The first one is just 1. The next one is 1 plus 2, which gives you 3. The next one after that is 1 plus 2 plus 3, which is 6. It's such a simple visual pattern, and it's the absolute foundation of our whole puzzle.
So, this leads us to a super useful formula. The nth triangular number, which we'll call Tn, is just the sum of all the whole numbers up to n. And there's this great little shortcut for it, n times n plus 1, all divided by 2. This formula, this is going to be a huge clue for us.
And what's really cool is that these numbers pop up in all sorts of unexpected places. Like, take a look at the famous Pascal's triangle. See that diagonal there? You got it. 1, 3, 6, 10. Our triangular numbers just hanging out. It's a great reminder of how connected everything in math really is. But for our puzzle, we got to get back to the algebra.
Okay, so we've got a handle on our triangular numbers. Now it's time to uncover our first major clue, and it comes in the form of a powerful, but actually really simple algebraic trick. This is what's going to let us rewrite our problem in a whole new and much easier way.
This is it. This is the absolute key to the whole thing. It looks a little weird, I know, but all it's saying is that we can take one fraction and split it into 2 separate fractions being subtracted from each other. And it's not magic, I promise. Let's just quickly walk through why it works.
Okay, so we start with the fraction on the left. Now, look at step 2. This is the really clever bit. That 1 on top, we can just rewrite it as n plus 1 minus n, because that equals 1, right? As soon as we do that, we can split the fraction into 2 parts, like you see in step 3. And then, the fun part. Things start canceling out, and we're left with exactly what we wanted. This little trick is the engine that's going to drive our solution.
So, we have our clue. Now we need to understand the mechanism that's going to put this clue to work for us. And that mechanism has a fantastic name, a telescoping series. The name is just perfect for what it does.
Think of it like one of those old-school collapsible spyglasses. It starts out long and extended, but when you push it together, poof, all the middle sections disappear, and you're just left with the 2 ends. A telescoping series does the exact same thing with numbers thanks to a chain reaction of cancellations.
Let's check out a really simple example. We've got 1 minus a half, plus a half, minus a third, plus a third, minus a fourth, and so on. You see the pattern here? Every single group has a negative fraction, and it's immediately followed by the exact same positive fraction in the next group.
And this is where the magic happens. The minus 1/2 gets zapped by the plus 1/2. The minus 1/3 gets canceled out by the plus 1/3, and this happens again and again and again forever down the line. It's like a domino effect of pure cancellation.
So after the whole telescope collapses, what are we left with? Just the very first term, which is 1, and the very last term? Well, since the series is infinite, that last fraction gets so incredibly tiny it's practically zero, so we don't even worry about it. The entire infinite sum just collapses down to 1. This idea is exactly what we need for our final step.
All right, this is it, the moment of truth. We have our suspects, the triangular numbers. We have our secret weapon, that algebraic trick. And we have our mechanism, the collapsing telescope series. It's time to put all the pieces together and solve this puzzle once and for all.
Okay, let's walk through it. Step 1, we start with our original problem. Then, in step 2, we swap in that handy formula for triangular numbers we found earlier. A little bit of fraction cleanup in step 3 lets us move that 2 up to the top. And finally, in step 4, a neat rule of sums lets us pull that constant 2 right out in front of the whole thing. Now, just look at what's left inside that sum.
And now for the big reveal. In step 5, we use our powerful algebraic trick, and boom, just like that, our sum is transformed into a perfect telescoping series. And we know what happens to that, right? That entire infinite sum just collapses all the way down to the number 1. Which leaves us with the final, beautiful, simple calculation in step 7, 2 times 1.
And there it is, 2. The answer we started with. We did it. We proved how an infinite number of fractions can perfectly, elegantly, and simply add up to exactly 2. It's just so cool.
And so, we've cracked the case. The infinite sum of the reciprocals of the triangular numbers equals 2. What started as a seemingly impossible problem has a beautifully simple solution.
Seeing a solution like this really makes you wonder, doesn't it? Math is just filled with these kinds of hidden patterns and jaw-dropping connections. It kind of leaves us with a final question. What other amazing secrets are just waiting out there to be discovered inside the world of the infinite?